Hello, I'm Matteo Provenzano from the graphics and gaming team at ARM, and today we're going to cover Vulkan best practice for mobile developer, which is a project we released at GDC on GitHub. But first, for a bit of context, what we do in our graphics and gaming team is help developer optimize their games on Mali, but on mobile in general, because most of the optimizations that are good for Mali are good for mobile GPUs in general. Now, this kind of work we do is twofold. A side of it is kind of one-to-one support for game developers or for game engines to try and help them optimize. And this can apply to any game developer. So if you have some query, just send us an email to developer@arm.com and we'll try to help as much as possible. But of course, we cannot reach everyone this way. So something else that we try to do is to write blog posts or sample code or basically any kind of resource that can help developer, that can help reach all developers, kind of broad, very broad audience. The problem with that is that we can have kind of a list, for example, of best practice that work on mobile, but it's kind of hard to digest for developers because they have to read the whole list and they have to remember that at all times. So that's why we try to bridge this kind of gap and release a project that is called Vulkan Best Practice for Mobile Developers. You can find it on GitHub. It consists of runnable samples which show both the good and the bad practice. You can toggle between the good and the bad practice using some buttons that you will see on screen. I have demos of that. Those come together with tutorials which explain the details of these good and bad practice, and there are also some kind of performance analysis. There is some kind of performance analysis built into the framework, which lets you see CPU and GPU counters just to see for yourself if the best practice actually gives some kind of improvement or not. Now I'll go over some of the samples we released, explaining what's the best practice in both cases and showing some kind of little videos to show the improvements. Just some extra information on the project. That's the link where you can find it. It is multi-platform, so it's mobile optimized, but it runs on Windows and Linux as well, even Mac. Also, we are having some kind of issue with multi-decay, but hopefully we will support it. You can see the hardware counters being displayed on device, and in our guides there is also some kind of explanation of how to use our tools. Now, moving on to the samples. First sample is about unbuffering, and the rationale behind having these as our first sample is to start from the first thing you set up when you set up Vulkan. And one of the very first things you have to do is to set up the swap chain. So which present mode should you use, and how many images should you ask for from your swap chain? There are two main presentation modes relevant for mobile. One of them is FIFO and the other one is Mailbox. I'll go through the pros and cons of choosing each of them so you can see for yourself why one of them is actually more optimal for mobile. In FIFO, as you can see in the image, there are 3 images that can be queued, 3 in this case, but it can be a variable number of images being queued for presentation. We have a queue for FIFO, it's basically the same. And the app is going to acquire an image from this queue, render to it, and then present. And when the app presents the images, it's sent back to the queue. So it's kind of released from the application's control. At every vSync signal, an image that is ready to be presented is going to be presented on screen, and after that, it's going to be released to the application again. So what happens here is that if the application is able to draw frames at a good enough frequency, it is going to be bound by the vSync signal because the queue is going to become full, and only at next vSync the application is going to be able to render the next frame. These might not seem like the ideal situation, but as you will see shortly, this helps avoiding unnecessary work, which is always good on mobile. So here's the alternative. It's Mailbox. As you can see, there is no FIFO anymore. There is no queue. There is just a single image that is queued for presentation. And if the app is able to render another image before that one is presented, the previously presentable image is going to be discarded. So the application in Mailbox mode can always acquire new images, can always render to them, can always present them. And the latest one, when the scene comes, is going to be presented. This has some kind of advantages in the sense that you can reduce input latency that way, because if you're going to have the latest input, you're going to draw the image based on the very latest inputs. But on mobile, that's rarely what you want, because the price you pay is that you keep submitting CPU and GPU work, which means they are both doing more work that's strictly necessary. You lose opportunities to reduce their frequencies, to let DVFS, that is dynamic voltage and frequency scaling, take effect. So you miss all the kind of opportunities that could help reduce your power, your energy, that is your battery consumption. And in general, if you're developing a game, your users will be able to play for kind of less time before the device overheats. So overall, we recommend FIFO. Regarding the number of images to ask the swap chain for, well, let's start with double buffering, because that might be the most intuitive way of seeing it. So you have two images, you draw to one of them while the other one is being presented, and then they are swapped. So the one you have drawn to goes on screen, and the other one, I mean, you can draw again. It's just plain double buffering, quite common. Now, in the current slide, you can see a case of double buffering working well. And this is when the CPU and GPU processing of an image takes less than the vsync interval. In this case, vsync is usually 60 frames per second on Android, so the interval is 16.6 milliseconds. If the image is rendered within that interval, all goes well. So we see the GPU renders the image, then it goes on screen, then the GPU renders again, then it goes on screen, and that's how it's supposed to work. Now, it gets interesting, and we start seeing issues if the GPU takes more than 16.6 milliseconds to render, as is the case in this slide. As you can see, the first GPU processing for image number 0 takes more than vsync. So we usually say that it misses vsync. And the presentation engine only has one option, that is to keep showing the same image on screen. And so the GPU will not be able to start more work until there is an image ready for acquisition. And that happens only at the next vsync. So effectively, even though we could have a frame rate that is slightly lower than 6 FPS, we could achieve that. But we are limited because of our double buffering to 30 FPS. This can be both a good and a bad thing. It's a good thing if that's exactly what you want. If you want to limit your app to kind of 30 FPS this way. But if you're aiming for 60, this is not really ideal, because you might see big frame rate drops that are just due to buffering, not to inherent limitations of your rendering pipeline. The solution to that is to move to triple buffering. And when you do that, you add another image that is ready to be rendered to. So as you see, the image number 0 misses vsync, but that's not a problem, because there is always an image ready to be acquired. That is image number 1 in this case, so the GPU can start rendering that, and then there will be image number 2 ready to be acquired. And so just by changing the number of option images, in this case, we can achieve a frame rate that goes from 30 to about 50 FPS. In order to just show you this effect in action, I'm going to show you a video. Before that, there is a little bit of detailed explanation here. You can use it. You can use this slide as reference in case you need those details for implementation. But it's basically when you call the gateway swap chain KHR, you should pass a minimum image count that tends to be the actual image count that you get, and you pass presentation mode that can be either FIFO or mailbox. You can see the difference here. These are both with FIFO, but one is with double buffering, one is with triple buffering. This is a common layout for all our samples. So you see a counter on top, that in this case is frame time, and on the bottom there are two radio buttons which let you switch between double and triple buffering to see the good and the bad practice. So right now it's on double buffering and the frame time has increased to 55 milliseconds. And at some point we will switch back to triple buffering and the frame time will drop again. So here's the switch to triple buffering and frame time goes down to 17 milliseconds again. So this makes a huge difference in terms of frame rate. Now, moving on to the next sample, pre-rotation. This one is quite tricky. It's quite counterintuitive and it's something that didn't apply to glass. It's quite new to Vulkan. It wasn't an application responsibility before that. So this might actually be kind of news to you. Rotation in mobile devices. Apparently it's straightforward. So you can see how you just want your phone to be rotated and you want to just render your scene in the same way, but just with a different aspect ratio. It will be quite intuitive. It will be just, you can think of it as like resizing a window on desktop. It shouldn't be such a big deal, but it actually is. The reason for that is that for the display processor, it makes no difference whether your phone is rotated in portrait mode or in landscape mode. The display processor will always use the same kind of axis to draw. So it's going to try and draw from top to bottom, left to right. But this applies to portrait. But if we go and rotate the phone, we can see that top to bottom, left to right now has a completely different meaning. And this is not going to work automatically. Something needs to be done to make sure that everything is rendered correctly, even though the phone has changed. So let's see the steps that are necessary to make sure that this rotation works properly. This is our scene in portrait mode. Now, we adjust the resolution to match landscape, but now the resolution doesn't match our display anymore. So we can adapt that by rotating the image so that now the axis that the display expects match the actual axis of our scene. And finally, what you get is that if we conceptually now rotate the phone, we see that the scene is rendered the way we expected. In order to further clarify that, we have this small animation. So first we adjust the resolution, then we rotate the scene, and then if you kind of rotate the phone itself, you can see that we get the actual scene we want. Now, this was the theory about explaining why there is a rotation at all when you kind of rotate your phone from landscape to portrait. Now the question is, who is going to perform this rotation? There is a major difference between glass and Vulkan in this case. The reason for that is that in glass, the driver was going to do this rotation for you in an efficient way, so you wouldn't have to worry about that. In Vulkan, in an attempt to increase the kind of transparency that the API provides, the driver is not allowed anymore to do this kind of magic to your image, which means that somebody else has to take care of that. It can be either your application or Android somehow. Now, let me explain more in detail. The kind of control you get with pre-rotation is that when you create your swap chain, you're going to be able to query it for the current rotation of the phone, and then pass a pre-transform parameter to the swap chain creation info. This pre-rotation parameter is going to tell the presentation system that either you are going to take care of this rotation or the presentation system has to take care of the rotation itself. Now, even if you have actually developed a Vulkan application, you might not have seen that in action. The reason for that is that typically in Android drivers we see there is no difference between correct and optimal ways to do that. Let me explain a bit more in detail. What you get when you try to see what transforms are supported are all possible transforms. So you don't see that one of them is the optimal one. That is the one where the application takes care of the transformation. So you might just want to pass pre-transform equals to identity. And if you do that, the rotation will be taken care of for you. Problem is that this has a performance cost. So there are two main ways in which this rotation might be taken care of. One of them is the optimal one. That is, if your application doesn't do that, then the display processor can take care of the rotation for you at the very end of the processing. But if the display processor doesn't have this kind of functionality, what happens is that the rotation has to be performed before the display. So the image has to be read from memory, rotated, and written back to memory. This is really bad in terms of bandwidth. This is not a GPU thing necessarily. It can be a separate hardware block. So it's not going to affect the resources of your GPU, but it's still going to affect memory bandwidth, which is kind of shared. It's kind of system bandwidth, and it's extra power and all those bad things we want to avoid. The trick is, or actually the tricky bit is that you cannot know if your phone actually has a smart enough display processor to take care of the rotation. So you don't know in general if this pre-rotation will have a bandwidth cost or not. In order to avoid all these kind of issues, what you can do is take care of the rotation yourself. So as you can see now, if you use the pre-rotation method we recommend, you're going to draw the image already rotated, and Android will have to do no work at all. It can just present the image as it is, and this is going to be the kind of most efficient way possible to handle that. This is all good, but it doesn't mean it's easy to do, because you actually have to draw the image in a kind of a rotated fashion. This tends to be a bit easier in applications with more complex rendering pipelines. The reason for that is that you don't need to touch any of your images. You can still render the way you were rendering already. You only have to draw the swaption image in a rotated way. And typically, if your rendering pipeline is complex, you will have just a final bleed to the swaption image. So if you rotate the bleed, you're going to be mostly fine. You might have to do some extra adjustments, but nothing huge really. It's a bit trickier if you're going to if you're going for a mobile optimized kind of forward rendering pipeline, where you render, where a big part, I'd say, of your rendering is directly to the swaption image, because in that case you have to kind of rotate your scene, you rotate your UV coordinates, and readbacks become really tricky. So it's not easy, but there is a big chance for a performance improvement. Now, this again is a slide to show to serve as kind of a reference. So if you want to apply this pre-rotation system, what you have to do is just to set the pre-transform to match the current transform you get from the presentation presentation engine when you try to create a swap chain. And here the result. So this is in a phone which doesn't have a display processor that is kind of smart enough to handle the rotation. And as you can see, the moment where we enable pre-rotate, we see a major saving in terms of external read stalls, which means that system bandwidth, the system memory bandwidth is kind of less stressed if the application takes care of the rotation itself. As a disclaimer, this video doesn't show a huge benefit, but that's due to the fact that the recording system we had to use, actually all the recording systems we tried in order to show that, would affect the results, because as you might imagine, our recording system is going to add another layer to your rendering pipeline, and so this pre-rotation is going to become a bit more. And of course, it only applies to devices which have no DPU support for pre-rotation. Moving on, the next sample is about load and store operation. This is a major issue on mobile, and it's quite interesting because the best practice for desktop or what makes sense for desktop might be really different than what makes sense for mobile. Now, you're probably familiar with the load operations. There are not many of them, and their meaning is quite straightforward. One of them is load, so load previous content you have in memory, clear, so clear the contents of your image, or just don't care if you are going to render on top of it anyway. Now, on desktop, you might just think that load would be free, in the sense that you already have the image there in memory, so you don't have to do any extra work for like clearing it. Kind of counterintuitively, on mobile, clear is much more efficient than load. This is due to an optimization that we can do with tile-based GPUs. That is, if you only need to clear a frame buffer, we don't need to fetch any information from memory. So we can start kind of rendering the tile from scratch without any memory accesses. If you instead ask for load, it means that the image has to be stored and loaded back from memory, and this is a big hit in terms of memory bandwidth. So if you are working with mobile, always consider doing clear or don't care. It actually doesn't matter for Mali. They're basically the same in terms of performance. And only load if you really, really, really need to. Pretty much the same for store. So the message is always don't store if you don't need to, because if you store, it's going to be kind of extra memory bandwidth to write the tile back to main memory. So whenever you can, just go with store off, don't care. And something you can even do on top of that is, for example, for a depth buffer, let's say you have a depth buffer that you only use for a single render pass. So you start by clearing the depth buffer. So as we saw in the previous slide, you're going to specify load op clear. Don't call pk command clear attachments, because that actually goes and clears the whole image in memory. So that means a lot of memory accesses. So you clear it with your load operation. And at the end, you do store operation, don't care. This is all good. So you only need it for that render pass. It's not going to be either read or written back to main memory. But something you might think is, why do we even have a depth buffer by that point? If you're not going to read from it, we are not going to write from it. So we might as well not have a depth buffer at all. And Vulkan has support for that. So you can ask for an image to be created from a lazily allocated memory, and the image should have the transient bit set. And if you do both of those things, and you don't read from it and you don't write from it, then the driver can avoid allocating that image at all, saving some significant, potentially significant amount of system memory. So yeah, don't load if you don't need to load, don't store if you don't need to store, and if you don't need an actual allocation for the image, just go with lazily allocated and transient. Now here's for the sample, which shows quite a nice benefit actually. So if your load operation is clear instead of load, we see a difference that can actually be computed to be exactly what you would expect. That is, you do the width by the height by the bytes per pixel, so you can compute the size in bytes of your color attachment. And then if you multiply that by the frames per second, you can kind of compute the bandwidth it will take to load that attachment for every render pass. And what we saw and what is highlighted in the tutorial is that the numbers actually match. So if you do the kind of computation, that's the difference you see in this sample when you move from load to clear. As a disclaimer, if the device you try it on has some kind of frame buffer compression, the results are going to be altered. The difference would be a bit smaller. But in this case, we didn't have frame buffer compression, so the difference you see is quite large and matches the theoretical one. Now, I wanted to briefly touch on another sample we have there. This one is Mali specific. It shows the benefits of AFPC, that is our frame buffer compression technology. And as you'll be able to see, when we tick the AFPC box, the external write bandwidth is going to go down. It's around 1 gig per second right now. And when we toggle AFPC, it's going to drop down to 800 to 900 megabytes per second, depending on the angle in which we're seeing. But in general, we see up to 35% saving in external write cycles thanks to AFBC. In terms of general observation you might have made on these ones, you might see that our bandwidth is quite high in general, and this is because this was with a previous version of our scenes which didn't use texture compression. So uncompressed textures are not really great for bandwidth. Please compress your textures, and now our framework actually supports that. And if you go and check out our new scenes, they all have compressed textures. This brings me to our next topic, which is our framework. We try to keep the samples as close to Vulkan as possible. So we really try to limit our framework to the bare minimum, so you can actually see what is going on in your Vulkan samples. We had to go for some kind of compromise, because if you keep it really low level, all the extra information, all the extra setup is going to kind of swamp whatever we are trying to show in the samples. So what we did is we built a framework which helps in creating all kind of Vulkan objects and in your kind of rendering loop, but it still kind of treats Vulkan objects. It still tries to let you use the actual native handles. It doesn't try to abstract out too much on top of Vulkan. So something we added was runtime GLSL shader generation plus reflection using Spear of Khronos. And we simplified the creation of some Vulkan objects such as render path, frame buffer, pipeline layout, descriptor set layout, plus we load 3D models in GLTF 2.0 format. Now this is a view of Vulkan object in general, like all the kinds of Vulkan objects you're going to need for rendering. You don't need to digest this whole slide, it's really complex, but the idea we want to convey is that some of these objects are kind of dependent on other objects. So there would be no point for us to show how to manually create all these objects when they can be kind of automatically generated or are kind of dependent on other objects. So we identified them. They are the ones highlighted in blue here. And what we did with our framework was to simplify the creation of these dependent objects. We have a kind of a bit higher level API, which lets you begin a render pass using a render pass and the frame buffer that are actual Vulkan objects. Then you bind resources. There are typically a graphics pipeline with its layout and the descriptor sets for the attachments you need in that pipeline. You're going to draw using vertex buffer and index buffers, and then you're going to end your render pass. The objects we are using are, there is a kind of a render context starting from the right, which has several frames. Each frame has frame-specific objects. It's quite useful in mobile to keep those separate from each other because these frames are going to run concurrently in your GPU. So if you don't share resources between them, you have an easier time ensuring that this pipeline keeps working and you don't have unwanted dependencies. Each of these render frames is made of several render targets, which in turn they're made of some color and or depth images along with their image views. This is how rendering looks like in the framework. So you begin a frame and a new image is acquired. You run all your render passes with your render target, resources, scene, whatever you want to do in your render pass, and at the end you present the image. An optimization we have not been making yet, but has come out quite a bit recently, is late acquire for the swap chain image. So something we might consider in the future is to move this acquire next image later in the frame, so we don't unnecessarily block at the beginning of the frame. We can do all kind of processing both on the CPU and on the GPU, which doesn't involve the swap chain image. We can do that earlier. Now, this was kind of a view of our framework at GTC when we released the project. But in those past 2 months, we have done several improvements to the framework, which are allowing us to build some more complex samples. And I just say they're allowing us to build more complex samples, but the idea is to allow everyone to build their own sample or to modify our ones. So one of the key ideas of our project is that you can take any of those samples, load a different scene, test out different beats, all this kind of stuff. It should be as easy as possible. And if it's not, just let us know. Just open an issue or a pull request if you want to make some contribution. We will be really happy to accept any contribution to the project. Now, in terms of general improvement, something I already mentioned is texture compression. We now support ASTC compressed textures with mipmaps. The decompression is relatively fast. So on desktop, where in cases where ASTC is not supported, we just do a quick decompression. And we also support KTX in terms of texture storage format. We have more scenes, and even more of them are upcoming. In our next release, we will actually release a couple of really nice internal scenes that were internal. We are now, releasing them publicly. So, yeah, keep an eye out for that. File system abstraction, in the sense that we don't have to have platform-specific code. We just have a single abstraction to access files on every platform. And as you see here in the screenshot, we have a nice debug window with a lot of information that didn't really fit into the UI. So our UI started being cramped, while we wanted it to be very simple, just the radio buttons that let you choose the options that are the most relevant to a single sample. Everything else, we are moving it to a separate window that you can bring up if you really want to look at the internals of what's going on in the sample. In terms of showing how our framework can be expanded, as a proof of concept, we did a port of Sasha Williams samples. On the right of this slide, you can see our kind of launcher that has both our samples under performance and in basic. There are the kind of more introductory level tutorials to API features that Sasha Williams made. They're available on GitHub. And as you can see, you can just launch them, go back and launch another one under the same launcher. I'll just let it run for a little bit so you can see the tessellation sample in this case. And our aim here while doing this proof of concept port was to maintain the integrity of the samples. So the code, we kept it as similar as possible as it was originally, because we didn't want to alter the main concepts that Sasha was telling, was the concept that Sasha was actually teaching with the samples. And yeah, just to show, this is one of our samples running under the same kind of framework. Another improvement we just recently made is profiling improvements. So our the best practice project uses HWC pipe for profiling. It's an open source library you can find on GitHub as well. It was originally made by Hans Christian when he was there, and we now maintain it. And we released a new version that has kind of an easier to use interface in case you want to integrate it in your project. So if you have a project and you want to get some CPU, GPU performance information, counters, you can now do it through a simple interface that you can see outlined here. It's about 5 lines. So you just start a profiling session. You ask for counters using an enum, so you can easily see a list of all counters that are available. You just call sample, you check if there are values, and you read them. And so this is the way that we use internally to get the data that we then show in those nice little graphs that lets you see any performance improvement or reduction. And something we have been working on recently is capturing data at intervals that are smaller than a frame. For example, getting data at 1 millisecond interval, continuously sampling and showing them on the graphs. This is quite important for some of the samples because you'll be able to see, for example, vertex and fragment work, and if that is correctly pipelined or not. So you can see if it overlaps, or rather if it's kind of serialized, which is a bad thing for mobile in general. These improvements are going to support our next samples. A few of them are in flight and they're going to be released soon, hopefully very soon, we'll see. And some more of them we have been brainstorming on what's the top priority, and we are going to start working on them pretty much right now. So in terms of samples in flight, we have three main ones. We have the pipeline caching one, which we want to show the benefits of actually using a pipeline cache and what you can do to ensure that your pipelines are reloaded when you load the scene. So you store all possible combinations of pipelines and you reload them at the beginning of your application. So then you don't have to do, well, depending on your game, you don't have to do too much of pipeline creation at runtime. We want to show the benefit of specialization constants versus uniform buffer in a kind of Uber shader sort of setting. And we want to see if, as we expect, specialization constants are as efficient as defines in terms of shader efficiency, in terms of behaving as if the specialization constant is set at compile time. And the compiler can actually optimize as much as we expect in that case. Workload synchronization pipeline barriers is about showing what happens if your barriers are not correct. For example, if you have your wait idle, it's going to be really, really bad for mobile because we don't want this kind of synchronization between vertex and fragment. We want them to be pipelined as much as possible. And we're going to show that if you set the right pipeline barriers, you can get that kind of pipelining going correctly. Something you might notice is that all of these might be straightforward advice if you're used to mobile or stuff that is clearly supposed to work. But an important bit here is that it's not enough for it to be clear or obvious to us or for us to just publish a document. We really want you to be able to try it for yourself on your phone and see if the data you get are the ones you expect. We want you to actually have proof that the best practices we recommend are actual best practice and remain best practices over the years, over phone generations, because of course the advice might change and this helps us see if there is need to update them, and it helps you in seeing that as well. So you might see if stuff changes and what you can do about that. In that case, we will update the best practice, of course, but it's easier to do in this kind of setting than with just a static document published online. In terms of next samples, we try to identify the areas where kind of developers could struggle the most while trying to set up an efficient Vulkan renderer. These are also the areas that we kind of struggled while learning Vulkan. Not because they are necessarily hard to use, but because you have so many options with them, and it's really hard to understand which is even supposed to be the most efficient one. So we would like to show samples which you can actually measure the most efficient approach. Some of them are command buffer reusing versus just allocating and freeing at every frame, the best way to do multi-threaded rendering, the best approach for deferred rendering. So if you're going to use render passes with subpasses, how you have to structure your gbuffer in order for it to be the most efficient possible for mobile, and how to manage your descriptors. So descriptor sets, descriptor pools, you're going to allocate and free, or you're going to keep a set of descriptors and update them every frame. You have countless options there. And again, we want to show which is the most efficient for mobile. Now, if you have ideas, please let us know. It's extremely useful to us to hear from you. So any feedback and any contributions are welcome. Just go on GitHub. The link is on the slide again. Feel free to open an issue, even just to ask a question. We'll be happy to help. We'll be happy to kind of advance the ecosystem in every way we can. So that's all I have for today. Thank you.